Right, so yes, so Hog asked me to talk about Bayesian hierarchical modeling, which is what that says there. You can read. Yes, the syllabus is here, the notes are there. But yeah, so this is obviously quite a broad topic. I don't know how familiar people are with it, but so I wanted to step through the like super basic stuff of it. What I wanted people to kind of take home at the end of it is to know what it is, right? To know how to use it. So I think it's a super useful technique. You've probably done it before without knowing. But basically how to build a hierarchical model, how to use features of it in order to inform how you simulate your data and infer your data. And yeah, right, so the majority of the beginning part of it is going to be on slides. There's going to be a little bit of kind of like work to do on the walls or on pads and paper. And then there is this Jupyter notebook, if we get to it, that kind of does some stuff that we can't do by hand. Right, so yeah, the first question we want to ask, right, is what is a Bayesian hierarchical model? So stepping through it word by word, right, so it's a model, right, so it's a probabilistic description of your data generating process. It's Bayesian because I'm Bayesian. I won't go into it in any more detail in case I rile anyone up. But it's the hierarchical part that people really care about here. That's the hierarchical part is the really important thing, right? And so kind of digging around online and looking at the people who really think about this deeply, there's not really one clear definition of what a hierarchical model is. To me, what it means is that the structure of the problem means that some of the parameters of your model have very, very different scopes, okay? So that you have parameters that describe your like individual objects or your individual observations. You have parameters that describe groups of objects, groups of observations. And you have this kind of hierarchical structure that builds up, that kind of naturally, well, especially in astrophysics, naturally kind of builds up. And so that you end up with things like, that you might have heard of, like nuisance or latent parameters, hyperparameters, normal parameters, all of these things that you might have heard of in the past. So another quite nice definition of this is by David Bly that says, essentially he defines a hierarchical model as a model in which inference about one unobserved quantity affects inference about another unobserved quantity. Roberto Trotta has a different way of thinking about it from a kind of physical perspective. It's just a way of separating the uncertainty that enters your data from the measurement process, from the kind of intrinsic physics. Personally, I don't necessarily find fluffy definitions particularly useful. I think it's much more useful to think of it from a kind of concrete physical perspective. And I think astrophysics in general is a really, well, it's a hierarchical science, right? And I really do think it's true to say that many or most astrophysical models are in fact hierarchical in nature, right? So I'm a cosmologist. When you think about cosmology, everything about it is hierarchical, right? You start with some parameters that describe the universe, you know, like how much dark energy, dark matter, stuff like that. These are the things that, as cosmologists, you really care about, okay? But what do they actually do? Well, they give you a universe that's populated with stuff, right? Galaxies, clusters of galaxies, you know, true objects that are actually in the universe that have some parameters that describe them, okay? But obviously you can't directly observe those parameters. You observe data that are generated by your measuring process. So you have this natural structure in there where you have some parameters that describe your, you know, the kind of overall structure of the universe. You have parameters that describe all of the things that you use to find out about the universe, all of your galaxies, all of your stars and things like that. Maybe you don't care about those actual parameters, but they're in your model. And then you have parameters that tell you about the measurements that you've made. And so obviously if you want to infer, if you want to learn about these things, you have to take your data and you have to learn about these things and you have to kind of pass things up the model. And so you have these very natural kind of hierarchical structures, right? You have different layers in your models. And this is not just a cosmological thing, right? So if you want to do something about, you know, finding out about the Milky Way potential, here you might have measurements of individual stars. Well, so you have like the Gaia data, then you have the stars that Gaia is actually looking at, and then you have your parameters that describe the galactic potential up at the top. And so, I mean, this is how hierarchy can arise in a physical sense of the model, okay? But you can also get hierarchies in observations, okay? So, again, from a cosmological perspective, you might have different instruments that observe the same thing, okay? So here we have, on the left-hand side, we've got WMAP versus Planck observing the cosmic microwave background, okay? But then you have different levels within these observations too, so maybe on the top you have different surveys. Here you might have different observation campaign with the same survey, okay? So this is like the Planck, WMAP 3-year versus 9-year results. But you also have, this is just a very simple example. And then within each instrument, you might then have different individual detectors, different frequency bands, things like that. And so even on the kind of observational side, you can rapidly build up this hierarchical structure. And again, this is not just something to do with the CMB. You know, you might observe specific stars in the galaxy or specific planets with different instruments, with different detectors. You might upgrade those detectors, but keep the same optics. And so you rapidly build up this hierarchical structure. And so if you want to kind of optimally infer the parameters that you really care about, you need to encode this hierarchical structure in your inference, right, using hierarchical models.
Steve, can I ask, so what makes a hierarchy? A hierarchy is the fact that there is like an inference process that is that,
so
or that you go from like more basic to...
Yeah, so I think it's that. I think it's the latter thing. I think it's the fact that, so it's like the scope of each parameter. So you might have a parameter that describes a specific instrument, right? You know, or a specific observation. So like the average noise on some observation that only pertains to that observation, right? Then you might have multiple observations of a specific star, but then you only have parameters, you know, then you have a set of parameters that pertain to that star, and then you might have some parameters that pertain to the population that that star is drawn from. And so the parameters describing the measurement, the star, and the population have very different scope. Yeah? That's how I choose to think about it. And that very much informs how I try and form and display my hierarchical models. It's not obvious. It's not always as obvious as that, which we'll see in a little bit. Yeah, please do ask questions, by the way, especially if I'm talking nonsense. Right. Yeah. So if we're going to optimally infer whatever we want to know about our model, we need to be able to, so capture this hierarchical structure in our model and use it to our advantage. The best way of doing that is to encode the model as something called a probabilistic graphical model or a directed acyclic graph. Right? Well, there's loads of like 3-letter acronyms for these things. It's a network diagram. It's a drawing. It's a drawing of your model, right? You might have seen these things around. Have you seen? Who has seen one of these before? Okay, cool. There are many, many ways of doing the same thing here, which we'll get to. But I'm going to go through the way that I do this, and then we can see some of the kind of menagerie of other ways that people do this in the past. Different people do it. So the specific physical model I'm going to talk about here is, imagine we have a population of standard candles, right? We just have a bunch of stars that all have this, supposedly all have the same intrinsic absolute magnitude, right? They should be the same luminosity, okay? Except maybe they're drawn, they're not all perfectly the same. There's some Gaussian scatter in their true magnitude, okay? And so we want to draw, we want to write down a hierarchical model that describes this, okay? So the way we're going to do it, we obviously have some observations of these things. And so we do this using a network diagram. We can go through it either way. So in this case, what we're talking about is that so we believe that there is a population that has a kind of true intrinsic absolute magnitude, but that actually there's some kind of scatter around it, right? And so there's some mean magnitude that these things all are drawn from, basically, and then there's some kind of Gaussian standard deviation around that. And so then we have some stars that have, that are drawn from this process that have their individual absolute magnitudes, and we have some noisy measurements of this. So to break it down, we have these things that are in circles here. These are kind of variables, right? These are unknowns that we might want to know something about. These are parameters. I've tried to separate them out into what I believe their hierarchy to be, and so we have parameters up here which pertain to the population. Then we have parameters here that pertain to individual objects, and that are indexed by their whatever index. The way that we denote there's a population, right, is with this box. It's called a plate. People often put varying amounts of information in here about how many things should be in there, or the indices that describe these objects. Things that we observe are going to be in double circles, okay? So these are kind of random observations, or noisy observations. And then things that are fixed, that are known, we're going to just denote with these little dots, okay? So this is a parameter that is known perfectly. This is an observable. These things in single circles, these are parameters of our model, okay? Now, there are a bunch of different ways of naming these things. It gets kind of complicated in hierarchical models. People often talk about these things as hyperparameters, these things as parameters, or latent parameters, or nuisance parameters, because probably you don't care about the properties of individual objects. You want to know something about the population. Yeah. Yeah.
What distinguishes the dot, the sigmas, from the double circle for the observed magnitudes when both of these are observed?
Yeah, they're probably both observed. This is just for simplicity's sake that I've put it there. But really, yeah, you would, I mean, exactly. I mean, if you're going to do everything all together, then this would be another kind of observable that you would kind of infer. Well,
so
in fact, it may well be a parameter that you would infer from your observables. Yeah.
Is the difference that the sigma doesn't inherit anything from a higher level parameter? The sigma's top of the hierarchy.
Which one? This one?
Yeah.
No, so the only reason that this is fixed is that I've assumed that it's known. That basically, say for example, you have some other calibration data set that you've observed, whatever, you can observe something on the sky where you can...
You wanted me to pull down the
I pressed the button. Essentially, all I'm saying here is that you know it before. So you could definitely write down a model where, in fact, you have like sigma hat here as another parameter that you can then infer from the observed magnitudes. I mean, really, this is the thing, right? I mean, this is a very simplified model. You don't observe magnitudes, you're going to observe fluxes. And so there's a whole ton of extra detail that you can put on here, and I'm going to build up some of that detail over the next few slides. But yeah, the other thing to say here is that all of these kind of links are put in here with some kind of directionality in them. The way that I choose to put them in is in terms of the kind of data generation process, right? So you need to know this in order to simulate this, essentially. And right at the top, just to be completely pedantic, I've also put in the fact that there's some kind of prior information that's going into our model, right? We believe that these are being drawn from some Gaussian process with these features. And so, yeah, I is just our prior information at this time. So I think I've gone through everything in here. Basically, the point being that, yeah, we have this population denoted by the plate, right? And so we actually have n star times these parameters. We have n star times these observables and these uncertainties. And then we have the kind of population level parameters there. Ooh, and the point being, so yeah, I made this stuff with some Dan Mackie Hogs code, which is quite fun. It's not fun, it's good. Okay, and so there's a very, very simple version of the model, right? And we can complicate this as much as we want. I've tried to come up with a few additional complications or additional ways of introducing structure that might be quite common. So The first one here being, what if we believe that our population isn't in fact pure, right? We're not observing one set of stars, we might be observing 2, 3, 4 sets of stars. Essentially we have some kind of outliers, we have a purity problem, okay? In this case, again, I've made it very simple such that these things are still standard candles, they just might be standard candles that have a slightly different intrinsic luminosity, or maybe they have a broader spread in their population distribution. And so instead now of having this simple case where we just have 2 of these hyperparameters, let's call them for now, we now have n-class number of those parameters. So we still have the same structure, we just have another population that we've put on the top here that describes the fact that we might have multiple classes of objects. Okay? And so these things still have a mean magnitude, they still have a spread, but now we have to add in another variable, which is essentially the fraction of these things that we think there are, right? So these pk things here should sum up to 1. And then within our little star box down here, we've also got to have a little tag, a little label that says, I belong to population k, okay? And so this is a Gaussian mixture model, so this is kind of nice because you can, people use this kind of stuff all the time. Maybe not with magnitudes, but it's a super useful tool. But you can complicate this even further because you might not have just one measurement of your star, you might have n-obs measurements of your star, and in fact this might vary from star to star. And so you can quite quickly not just build up different independent populations, but also different nested populations here, where you have populations within populations, blah, 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 all of this stuff. And so the point that I think Hogg wanted me to make here is the fact that things can get complicated very quickly. And it is super helpful for yourself and for anyone who ends up reading your paper that you be as pedantic as possible, which is something that comes quite naturally to me. Maybe not to all people. But yeah, right, so, having one of these diagrams is super helpful. So before I started doing hierarchical modeling before I realized that was what I was doing. There's an analogy in there somewhere, but I could only think of really weird ones, so I won't. But yeah, so I have hierarchical modeling papers where I don't have these diagrams, where actually if you come along afterwards and write down the diagram, then suddenly everything becomes quite clear about how you're actually doing your inference and how you're generating your data and things like that. As I'll show you in a couple of slides' time, there are many different ways of doing this, and so it's very helpful if you actually explain exactly what you've done here, explain the fact that this red square is a population, this circle here is a latent variable, this whatever is an actual variable, this is an observation, stuff like that. And yeah, list all of your variables that you have, put them in a table somewhere, list all of the distributions that you're using to kind of describe these links, which is something I should talk about, sorry. So yeah, I said that these links are in here showing how essentially one parameter then informs the next one. What these things really are, these are probability distributions, okay? So except for when you're going from a fixed parameter here, which is just a kind of, this is essentially well, actually no, that's probably not true. We'll get to that. Each one of these links basically encodes a kind of PDF that tells you about, how does this parameter depend on any of these. And so that was what I wanted to say next was, I find it super useful to be as pedantic as possible, and so actually put in the forms of these distributions, or at least put the distributions into your hierarchical model. And so you can see that it makes this thing kind of explode. It makes the network diagram quite cluttered, but it's extraordinarily useful in what's to come. Okay? For a wide variety of reasons. Firstly, it's telling you on this diagram everything that you need to specify in order to completely describe your model. Okay? So it tells you all of the parameters that are in your model, right, which is what we already had, but it also tells you all of the probabilistic relations between the parameters. And so you have to come up with forms for each of these distributions in order to fully describe your model, okay? And so in this case, what we have here are, we have some priors, right? We have our prior information, whatever it is, our beliefs about the model. Maybe it's some, well, it's prior information that's telling us how we expect the true absolute magnitudes, their true sigmas, the class probabilities, how we expect those to come from the model in the first place. Then we're showing how each object's absolute magnitude is drawn from the parameters that it depends on. So this is going to be probably a Gaussian process, okay? So each object's absolute magnitude depends on the class's mean, the class's sigma, all this stuff, and then from the kind of this is like a data generation step. How do our observations depend on the true underlying absolute magnitude and the measurement uncertainty? Okay. Yes, right. And so all of these things you may note are conditional distributions, right? So this is saying, you know, essentially it's telling you what does this quantity depend on. This is a complete list of things that you have to specify in order to simulate that, to generate a draw from that or something like that. Yeah, the specific forms of those distributions will heavily inform how you end up doing the inference of your model. Okay. So like I said, you have to choose these things, right? And you're free to choose them as you wish, right? So your Bayesian, everything's subjective. You get to choose something. Obviously, everybody else in the world gets to criticize you for your choices, which is really fun. And so you normally want to make these as, you know, as true to life as possible. But it's important to realize that might not be the best thing to do, okay? Or it might not be possible to do that. And you might want to consider putting in distributions here, or even reparameterizing your model slightly to kind of loosen its accuracy in some sense in order to make it actually tractable. But that's, you know, I guess well, I'll come back to that later. So this is a very simple example I've told you about here, right? This is some kind of Gaussian mixture model of a bunch of different populations with different absolute magnitudes or different standard candles. There's a lot of examples of this in the literature, and like I said, right, there's a number of different ways of setting out these diagrams, of actually describing what the different components of them are. Is anybody on either of these papers? No, I'm not going to criticize them. So on the left, this is one of Justin's papers. This is what made me start drawing hierarchical models in the first place, but they're not as pretty as his, never mind. So this is quite similar to what I draw, except for the fact that for some reason he doesn't differentiate the data from the parameters. But he has got all of this, the distributions in there, and he has set it out so that the kind of hierarchy is explicit. So this is for gravitational weak lensing analysis, right? Okay.
So in your scheme, there would be a double circle around the.
Right, exactly. So I would have a double. Yeah, exactly. I would have a double circle in there. But so basically, so this is so this is gravitational weak lensing. In fact, it's also, so basically here you have, what do you have? You have some cosmological stuff that gives you, so you have some cosmological parameters here which give you some true field, is presumably something like a dark matter field, okay? And then you have some galactic like measurements. So basically you have, what do you have? You have shear and redshift for these objects, or in fact maybe even just number counts in this case you might be doing. Maybe this is number counts, not shear. Anyway, it doesn't really matter. Basically you have your cosmological parameters, and then you have parameters that describe your instrumental noise, and you have parameters that describe your galaxy characteristics. And so these are all kind of higher level population, maybe hyperparameters you want to call them. And then, yeah, you have the kind of true things, so true features of galaxies, true dark matter density at a place in the universe, true redshift to that galaxy. And then at the bottom here, you have your observations, and then you have all of these links in between them.
They just didn't put their uncertainties because they're simplifying the diagram?
Right, exactly. So this is what I'm saying. Yeah, it's very helpful to be pedantic and include absolutely everything in there, but it's not necessarily the cleanest presentation. And so it's quite often, people often leave off things like measurement uncertainties that are fixed because it's just extra information that you're conditioning on in the end. So it's kind of up to you. I mean, I've included everything in everything that I've put in here to try and be completely open about, you know, everything. But potentially, I mean, I really like this diagram. I think it's super clean. And I think that at least once you know about things, you will know that this has some uncertainty in it that you know you care about too.
So can you remind us what the curly brackets mean?
Sorry? Oh, in this case, curly brackets is probably it'll just be like a vector. So it's so anything that's bold in here is a vector, but then you might have each galaxy might have a vector of parameters associated with it. So you could have put that in as a matrix, but it's the curly brackets in this. Is that what you're talking about?
Yeah.
Yeah. It's just saying for each galaxy, I might have a vector of parameters that I measure. So this is one way of doing things. There's also what I think is the complete opposite end of the spectrum here, where so this is a supernova paper where the hierarchy, I think, is not necessarily as easy to put down on the page, and so it's much more a case of just getting everything on there and bunging it all together. And just to show you, it's just to demonstrate that people do things different ways. In this case, the diamonds are fixed quantities. Like before, these double circles are observable. Anything that's in a round circle, like before, is a single circle is just a parameter, and that these plates are slightly different. But in both of these cases, the structure of the model is described in the paper, and so it doesn't matter. Right? It doesn't matter how you present it, as long as it's described in there. Other people have done this stuff. So what's this? This is some Gaia model. This is looking for period luminosity relations for RR Lyrae stars using Gaia data. And again, the hierarchical structure is not in there, but all of the links are. They've used slightly different terminology. So anything that is in yellow is a nuisance parameter. Anything that's in green is something that you care about. These double circles are thingies, data. And one of Boris's papers about photometric redshifts, where instead of doing specific parameters, there's groups of parameters are kind of lumped together into something a little more schematic. And just to get back to the point of things being complicated and having to make choices about how you set out your model. So this is something a Hug likes to complain about. About the fact that they designed their code to make nice, pretty, clean diagrams that would make things clear, and then I did this with it. So this is a model for the Cepheid distance ladder, right? So this is essentially trying to find out what the Hubble constant is by looking at Cepheid stars and supernovae. Okay, so what you want to do is you want to find a set of Cepheids where you know their distance. That allows you to calibrate essentially their intrinsic absolute magnitude. These things then have a period luminosity relation, right? So they pulsate, and the period of that pulsation tells you what their intrinsic luminosity is. So they're useful standard candles, but you can't see them quite far enough in order to probe the Hubble flow. And so what you basically do is you find galaxies that have Cepheids in that also have a supernova in, type 1a supernova, which then is a standardizable candle, but it's something that you can see out into the Hubble flow. So you basically have to chain together populations of objects. And so what we have here are anything in red is a population of Cepheid stars. Okay? Anything in blue is like a galaxy. And so at the bottom here we have galaxies where we have, you might not be able to see it, this is a distance constraint, but they also have a population of Cepheids. Then we have these things in these galaxies, the blue square here, that have a population of Cepheids and a supernova. And then further away, we just have galaxies that have a single supernova in them, and that basically gives us, essentially, as you can see, you just bubble all of this stuff up here and you get H naught out of the end. It's dead simple. But so this is what, this is probably not even, well, this isn't the full model, okay? But it is a full model of the data collected by the Shoes team, led by Adam Rees. But this is what we actually use to do the inference, and you can see that there's some simplifications that have been made. Partly this is because of the way that the data are presented. So in here we have observed periods and observed metallicities for Cepheids. These things are given to us without error, and so we can't have these true parameters in there. We basically assume that they're fixed, so they disappear. And there's a bunch of different choices that are made essentially to make the analysis tractable. And so this is just to kind of drive the point home that you might think that the physics is like this, but the way that you've taken your data or the way that you were able to infer or like actually analyze your data means that you might have to make some changes to the structure of your model. And in fact, this is what the Shoes team do, but that's another story for another time.
Steve, can I ask a slightly off-topic question on your things? I guess you use graphics to make these plots. Is that correct?
I use this daft PGM code that Hog and CFM wrote.
Okay, this one is. Okay.
Yeah.
And that uses graphics underneath, do you know? Or?
I have no idea what it uses, but there's I'll put the slides up. This is the link to it. I actually use, so if you do, to get these things in here, you have to, someone put like a pull request in, so you have to like do your own version of it, but it's nice.
Thanks.
Yeah, right, okay. So, for the rest of what we're going to talk about, we're going to use a simple astrophysical example, okay? Which is inferring the properties of Cepheid period luminosity relations, okay? So like I said, Cepheids are pulsating variable stars, and the periods of their pulsation is related to their intrinsic luminosity, right? So they're interesting objects to look at. And so you can write down, so this is people call it the period luminosity relation, or it's the Leavitt law, whatever. So this is Henrietta Leavitt's plot from like 100 and something years ago, showing how if you plot the log period of these objects against their magnitude, so this is like the maximum magnitude versus the minimum, then you see this kind of super clear relation, which is pretty cool. And so you can write this down in quite a simple way to say that the observed apparent magnitude of these Cepheids is their distance modulus, some intrinsic absolute magnitude, a slope for their log period, and then there's some intrinsic scatter about this. This isn't a perfect process, and so you can model the intrinsic scatter as essentially Gaussian deviations away from this mean relation with some standard deviation sigma int, okay? For the non-stellar astrophysicists or in the audience, the distance modulus is it's essentially the logarithm of the of the distance, okay? And so this is actually encoded in this stuff here, but we're going to do a very simple version of it, okay? Like I said, we're going to do a Gaussian intrinsic scatter, and in fact, we're going to assume that everything about this model is Gaussian. Okay, and so this is the first thing that I wanted you to do. I don't know why I wrote send. It makes it look really dirty, but like, woo, such a late thing. What I would like you to do, what do I actually want you to do in this case? Yeah, I want you to draw this network diagram for this model, okay? And you can do it wherever you want to do it. You can do it on the walls. So there's pens at the back. There's pads of paper. You can write it on your hand. You can do it in your head. But essentially, what we want to do here, right? So we have, like I said before, let's assume we have some set of galaxies. Each galaxy has some set of stars in it, right? So we have n stars per galaxy. We want to have the same slope and the same intercept. So these parameters are common to all stars in all galaxies, okay? We're going to assume for now that obviously each galaxy might be at a different distance and that we have some constraint on those distances for each galaxy, or distance moduli in these cases. And for simplicity's sake, we're just going to assume that these things are perfectly measured, okay? And yes, that we have this Gaussian intrinsic scatter. So, go for it. I may not have given you enough information to do this. If there's anything that I can display on this screen that is more informative for you to do this than this big censored diagram, and not the answer, then tell me. But like, let's just take a couple of minutes and try and draw these things out, okay? I'm happy to like write a list of the parameters that should be included in your model if that's helpful, or. You can work together. That's the other thing. Oh, yeah, sorry, so that's a good point. Sorry, so I've used I here to index the galaxy, and J is just the star in that galaxy.
Same number of Cepheids.
Yeah, but I know. So you can complicate this if you want. You can make n star have a I index if you want, but that's just showing off.
In any event, S and mu.
So S
is what we
this,
want.
so this is the yeah, exactly, right. So the things that we want out in the end are going to be this apparent, this true, whatever, intrinsic absolute magnitude and the slope. Yeah. Yeah.
Yeah, we did.
So this is the parameters of measure of the pole.
Yeah.
Or it's perfectly known as that it's the double circle.
So you have Mij, which is magnitude of
You want to assume
you have
there's no outliers. You know they're all Cepheids.
You have more than that, right?
Yeah, so just one
You have
class. They're all Cepheids.
You have time.
I don't think, I assume that it's the mean magnitude.
Yeah.
They're confusing. It's the mean magnitude, so it is the log of material. Or the maximum.
No, you already have the PA.
Yeah, I'm assuming that someone's done the like bit.
Sorry. Yeah, so I just wanted to coordinate one diagram. Yeah, so basically, yeah, so you have n galaxies. Each galaxy contains n star Cepheids, same with the galaxies, simplistic. And each one of these Cepheids, you have some measured apparent magnitude. You have a perfectly measured period. So all of the Cepheids are drawn from a population that has the same absolute magnitude and the same slope. So like each galaxy has a set of Cepheids that have measured apparent magnitudes and periods. Each galaxy also has its own distance, and it has a distance estimate to it for now. Let's just assume that. And then the whole thing is drawn from a population that has parameters, yeah, and some intrinsic scattering. Okay.
Like the true magnitude, the true measured
So
magnitude.
mu I is that?
Yeah, so mu I is constant for each galaxy.
Got that one up there. I like that one.
P is known perfectly.
Yeah, you just log P is known perfectly for every
So,
star.
I mean, I'm thinking,
So you can typically measure that with
So n star
very
is
small uncertainty.
Are we assuming that the period and the magnitude are perfectly measured and it's the intrinsic
M
variability?
star is the.
No, so let's assume that is perfectly measured, but not that.
And
So
sigma,
the apparent magnitudes are noisy.
Both in instrumental uncertainty and MIJ and also
Intrinsic scatter. Yeah, exactly.
They're gonna have arrows pointing to MIJ. Yeah.
so sigma's known perfectly, or
Which one?
sigma intrinsic?
Yeah. You can put priors on that if you want, but so in the version that I'm going to show you, that's fixed. That's known. But that's just for simplicity's sake. You definitely wouldn't know
The
that.
periods don't depend on the distance. But I think the measured magnitude. But yeah, I'm not sure if the arrow should flow. I'm not float out. I just feel like I'm missing circles. Like there's three maps.
They're gonna be calling everything. Well, so for
This
every
function that you want us to complete, should you return like only one?
Oh, you jumping ahead?
Noise.
Oh, is this not what we're doing?
No.
Oh.
This is just writing it down for now. Writing down the network diagram. That's cool. How far ahead of us are you?
No, actually, I feel like I'm a bit more comfortable. He's already like written the code to run the model.
Yeah, I'm leaving. I'm finished now.
No, but I'm completely.
But we don't know the measurement error.
I think
We're supposed to assume it's the same, there's a Gaussian distribution.
Yeah, so in the model that I've assumed that every star has the same measurement uncertainty on it.
And that it has to be determined.
No, that's known.
Oh, okay.
You can
that's
assume
a
it's
classic
known. Yeah.
I think so, because you might not know the
It's a
scatter.
nuisance problem.
I mean, the assumption here is that this is a Gaussian or something.
Let's call that sigma m or something.
Yeah.
Yeah.
Oh, yeah, I mean,
Oh, that's the intrinsic scatter at the period.
Well, like this presumably, well, this is fixed unless this comes with some uncertainty too, right? So there's sigma, mu, hold on.
the other one you wrote like, well, off M star magnitude, off
Right.
MIJ given
N star, yeah.
sigma in.
Because I think, yeah, this goes here, the P I M I J given mu, given M, given S.
Yeah.
Right, like, those are all joint. I'm gonna roll with that.
Final answer.
So assume that you have a measurement of that, but an uncertain measurement.
Oh, it's an uncertain. So the uncertain things, that's the only uncertainty in the measure.
So this is not known. So this is measured noisily. That's measured
But
noisily,
you know
and
the
that
noise
is
on
measured
both of them.
perfectly. But you know the noise on both of
And
them.
what you don't know is epsilon.
Yeah.
Yeah, because group stars.
M star.
Yeah.
What are mu and M star?
Yeah.
So mu. Yeah. Right. Okay. Sorry. Mu is the distance modulus. So that's the distance to the galaxy, basically.
That's what I told them.
M star is like the intercept of the period luminosity relation. So it's like
Yeah.
in this case it would be the period of a 1 day Cepheid.
Okay.
Sorry, magnitude of a 1 day Cepheid. Absolute magnitude of a 1 day Cepheid.
How is that known?
Sorry,
How is that known?
it's not known. So this is something you want to
We don't
infer.
use Zephyrs to.
So you want to infer this, you can infer this, and this is known, uncertain, sorry, perfect measurement,
Oh, I see.
uncertain,
And then you're trying to
uncertain
infer
measurement.
the
And then, yeah, and
properties
then-
also.
Okay.
Oh, I
I
see.
think that's the part of the problem.
So does anyone have a finished model? I can see one. I can see something at the back. How's everybody getting on? Anyone finished? Anybody need help?
Something, but I don't think it's right.
Okay. I hadn't really thought about how to do this now. So does anyone want to show us what they've got, or is that like too embarrassing?
I can't draw the picture.
Or do you want me to just show you what mine is, and you can compare, and I'll ask you if you've got the same thing, and you'll say yeah. Okay. So are we ready? This is the unblinding moment. No, it's not. Where's it gone? Hey, there we go. Okay. So it's a bit stretchy because of what we're going to do next. But so we have two populations, just like this one at the back, right? Okay, so we've got a population of Cepheids per galaxy, right? That has index J and has n stars, and so we're weirdly assuming that we only observe galaxies that have exactly the same number of Cepheids in. Then we have another box, which is the number of galaxies that we have. Okay, our noisy observables that we have a distance modulus estimate for each galaxy. We have a apparent magnitude estimate for each Cepheid. Okay, and then we have these perfectly well-known periods. Okay, they're a bit weird, right? Because really they're data. They should probably be down here, but they're perfectly known, so it's a bit of a weird thing. And so we have some uncertainties on the, I've indexed these, so maybe the uncertainties on the magnitudes are all different for all the Cepheids, different for all of the galaxies for their distance modeling, okay? We step up the hierarchy, we also have a true apparent magnitude per star, and we have a true distance modulus per galaxy, okay? And then if we step up the hierarchy again, then we have these period luminosity relations, so we have a perfectly known sigma int, whatever reason I chose to do it. Well, okay, this is for algorithmic purposes that I've chosen it to be perfectly known, but actually it's more like that at the back, where you don't know this and you want to infer it too. So we have a slope, an intercept, and a scatter, right? And then to be completely pedantic, I've also put the kind of prior information that we have for those parameters, where if we assume that these things are drawn from Gaussian distributions, then each one of these things has its own mean and width to them, okay? Did anyone get anything that looked like that? That one at the back looks quite a lot like it, I think.
The confusing thing is like we missed the middle level, like the true value, like the true value of the apparent magnitude is kind of confusing to me.
Right, okay.
I guess I understand, like you have a noisy measurement of what the actual flux, what the actual magnitude was.
Yeah.
Okay.
Yeah.
And that actual magnitude is what's related to the, with the slope and the period.
Yeah, exactly. So you can think of it as because this thing has intrinsic scatter in it, your population has some kind of mean and width to it. But then in order to take it, to basically draw a single object from that population, you do a draw from that Gaussian distribution. That gives you its true apparent magnitude. That gives it its true absolute magnitude, and then the distance of the galaxy gives you its true apparent magnitude. Okay, so you really do have these latent parameters in there. Sorry,
Can you expand a bit on? I think it's related to what you just said, but can you expand on the difference between sigma mu I at the very bottom and sigma mu and mu bar above it?
Yeah. So for this diagram here, I've assumed that these things are drawn from Gaussian priors, and so these are the parameters that describe that prior. So for the distance modulus, that's a really weird thing to think, right? You know, it actually comes from cosmology in the end, right? Because you have some kind of like you're basically drawing from a volume element that depends on your cosmological parameters. And so this thing nearby will actually go up as z squared, whatever. For simplicity's sake, for the next steps that we're going to do, I've assumed that this is a Gaussian. And so this sigma mu here is the width of that prior distribution. This sigma mu hat I down there is the uncertainty on the Gaussian estimate of that distance modulus. Yeah?
It's the measurement error, and the
That's
others are the spread of the distribution.
Exactly. And so I mean, this is a really simple version of the model anyway, but you would expect this to be much larger than this, okay? Otherwise, you're not learning anything, right? This uncertainty is informing all of this other stuff.
But it seems inconsistent with what you told us, that the sigma int isn't in a big circle, but it wouldn't have any arrows into it, right? Given what you told
right.
us, that it's an unknown thing.
No. So here I've assumed that it's known, okay?
But how would you know it?
Yeah, so that's
If you
exactly.
don't know the relationship, how could you possibly know it?
You would have to infer it at the same time.
Right.
No, and so
if
that's
that were the case, the only difference would be that the circle would be big, because
Exactly.
you wouldn't have anything, arrows coming into it.
no. So you would have arrows. So if you didn't know what this was, you would have it in a big circle, like you're saying, and then you would have some prior on it as well. Because it's a
I don't know how you would have a prior on it.
on sigma int. In what sense? So you might, well, so the standard way of doing it is you have some kind of Jeffreys prior, so you have some, it would be something like 1 over sigma int or 1 over sigma int squared. Like essentially so that would.
It's not an assumed mean value or anything like that.
No.
Just
So this would be,
an
it's
assumption about the
no-
distribution.
Yeah, exactly, right? Yeah, exactly. So in this case, because it's a scale parameter, you would say something like it's logarithmic, right? You don't know what, it's evenly distributed in decades of size or something.
It's essentially on the functional form.
Exactly. Unless you actually had some physics, right, that said all whatever opacities in Cepheid atmospheres mean that we expect this to, or whatever, the effects of metallicity, all of this stuff, right? Yeah. Yes.
You were just mentioning this before, but would it make sense to add another circle that was just from m star and sigma int, that was the true absolute magnitude of the Cepheid, and then have that circle that combines the mu to get the...
Right, exactly. So there is a kind of fundamental, there's a degeneracy here insofar as you could put in capital Mij, right, which is then it would have a deterministic link with one of these two things, because yeah, so you could definitely put in so if you put in capital Mij here, drop that link and put it in there.
Or I was thinking, like, you have two arrows going from m star and sigma int to lowercase m, but those two really just go to capital M, right? So like,
yeah.
And then only from capital M, then you need mu and s to get you to.
No, so the slope.
I guess the question is, when you have these deterministic relations, like you're saying, what do you choose to call variables, and what do you
Right. So you're free to do it, whatever makes sense, and so yeah, that's a really good question. So the question there is, you could have parameterized this in terms of a capital M, so like an absolute magnitude, right? So that you have an absolute magnitude that's drawn from this distribution, basically, that doesn't care about the distance. The distance only comes in when you go to apparent magnitudes. And so you can actually structure this diagram like in a different way. You're free to choose what that is. And so if it makes more sense, it might make more sense to code it up a specific way, in which case you might want to change the way you do this. But like, yeah, no, you're free to choose it, basically. And so in they have that in here. So this is the supernova cosmology one, right? So in here you have you're saying that your type 1a, so well, you know all this stuff, right? That your type 1a supernova has some intrinsic scatter rate at the V band magnitude. And so then you have, in here, they have their random variable as the absolute magnitude. And then you have this deterministic relation to the apparent magnitude that has your distance modulus in it. So they've just chosen to parameterize it a different way.
But putting putting m star and sigma int together, leaving out s, actually wouldn't, I don't think,
No, so you have to have...
Because it could be that epsilon might be, for instance, dependent on s and m star because of some higher order correction.
Right.
To the simple
Yeah, exactly. So the way that you would want to do it depends on how you expect your model to develop and on all of these things.
Well, it seems like it depends on what the uncertainties are actually on.
Right.
Yeah.
Mm-hmm.
Or what's causing the intrinsic scattering.
Exactly,
Right.
exactly. Yeah.
And it might be
Right.
very strongly
Which could
related to
depend
M
on the
star, or
physics.
maybe it actually depends on P.
Yeah.
Right. Right. Okay. So there's another task here, which is now basically just to take this and fill in these gaps. So put in the probability distributions that govern these uncertain links, okay? And so you can just start from this. And so anywhere where there is, well, yeah, we'll see. I mean, if you these are the things that seem immensely clear when I wrote them down, but clearly aren't now. Basically, any of the links between these kind of levels in the hierarchy need to have a distribution in them. And so here you have basically the intrinsic scatter distribution, okay? Here, this is going from a true magnitude to an observed one, so this is a likelihood, right? This is a noisy likelihood. And here you're going from a true distance modulus to a noisy observed distance modulus, okay? So those are the things that you have to plug in. You have a, noisy period luminosity that is encoding basically all of these links in here, okay? Then you have a likelihood and another likelihood, so. Yeah, and I don't know if you want to know what the notation is. But yeah, did I put any extra information on there? No, okay.
Can I ask a question?
Yes.
From the ceiling. If there was covariance between any of the observables, how do you deal with that in a plate?
If there's covariance between, is there a specific? So the covariance is encoded in the PDFs that we're going to put in. I don't know why I'm looking at the roof. Yeah, it's in those PDFs. Okay. So if they are perfectly if it's perfectly deterministic, then that goes back to that conversation we were just having about how you structure this model. And you can explicitly put them in there if you want to, put them in as like a fixed parameter or have some kind of different way that you draw these links to show that it's a deterministic relation. But if there's a probabilistic thing in there, and if they're not perfectly correlated, then yeah, then you can have them in as separate unknown variables that are then related by that correlates, like a probabilistic distribution encoding that correlation. Does that make sense?
I'm really kind of asking more of like a nomenclature question. Like, for instance, those sigma MIJs, right? If that was actually a covariance matrix, not individual error bars.
Yeah. Well, in that case. Yeah, right.
What would you drop the plate? Do you just have to not use a plate if you want to represent a full covariance matrix?
Yeah, exactly. You kind of move it out, right? So that then you would have some capital sigma underscore I or something like that. So then you would have a covariance matrix per galaxy. Or if it was over all IJs, then just move it out onto this side so that it's outside these two plates.
All right, that makes sense. Thank you.
Yeah, but I think you have to write.
So has everyone done this, or has anyone done this, or not? No.
Two boxes.
Two boxes. You need three.
The other.
Yeah, that's like the prior audience, right?
Yeah.
So
And then P of M. P of M.
I think it's just P of the thing and the arrows are pointing to, given the things that all the arrows are coming from.
Like differentiations, group based.
Well, I mean, supposedly the big advantage of this is once you write it down, it's actually automatic to get rid of
Yeah, I think like all that's for pi standouts.
Has anyone finished drawing what's on the board yet? Just get pens and come and draw it on here. And Yeah, no, exactly. This is duplication of effort. So, just to kind of go over it again, we have noisy measurements of these distance moduli that only depend on the true measurement of the distance modulus and the uncertainty, right? So we have some kind of probability that depends, it's the probability of this given this and that. On the likelihood side, we have something similar, right? So we have a probability of this object given this and that. And then for the true values, this is, what's the probability of getting some apparent magnitude given distances, true period luminosity parameters, and scatter.
Stephen, are you asking for like the actual functional forms, or
no, not the functional form, just like probability of x given y.
So how is it any different than probability of the thing in the circle given all the arrows coming from it?
It's not.
Ah! That's why we were confused.
So what is it?
What is it? Does anyone, can I show you the answer? Or?
Yes. Sure.
Okay. So it's just this. Oh yeah, sorry, I forgot about the priors. Never mind, sorry. Yeah, so this is very easy, right? So here we have the probability of the observed distance moduli given the true ones and the I've bugged this diagram up, and the uncertainty. So these links really should go in there. Okay, can you just turn those? And so then you have your probability of your observed apparent magnitudes given the true ones and those uncertainties. And again, this arrow should go up there. Sorry, I'll fix that. Then you have, this is your intrinsic scattering in the Cepheid period luminosity relation. So this is the probability of getting a true apparent magnitude given a distance modulus, the kind of intercept and the slope and these log periods and the intrinsic scatter. And then you have each one of these prior distributions that's just telling you what's the probability of drawing some true distance modulus given your prior assumptions on those things. So does that make sense?
Yep.
Could you do it again if you had a model that you that you wanted to do inference on? Not yet. Well, hopefully it will help. So I'll put these online so you don't need to, and so I'll fix that and I'll put these online so you don't need to.
Just to understand, the actual values of the sigma mu hat and sigma m hat of my j's, which are represented by the dots, are nuisance parameters. Is that right?
These things?
Yes.
Well, right. So in this example, I've assumed that they're perfectly known, so they're just kind of
external knowledge. So
exactly.
That's the symbol.
Yeah, so it's fixed. Yeah, exactly. So these things are fixed. So you can assume that we have calibrated these uncertainties somewhere else.
And so those should be aiming into the orange box.
Exactly. So exactly. Yeah.
And bypass.
Yeah. Okay.
It's not like you're flipping the arrow.
Yeah. No. So this is just showing the kind of flow of information, I suppose. Yeah. Because you know this.
That arrow I understand. I'd be happy with the other arrows. But then I'm confused about the arrow going from the orange box down to the observable. There's a choice of how you want to think about it, I guess, which way you do that arrow.
Yeah, exactly.
And so is this a standard choice, or is it
I don't know. This is what I do. I think it's the standard choice insofar as you're kind of coming down through. So the way that so it's kind of on the next slide. So I've drawn this the way that you would simulate the data. So the arrows go from basically in the order of how you would generate a realization of this data set. So you would take your kind of priors and you would draw some true values, and then you take your priors and you draw some true distances, and then you take all of that information that allows you to get some true magnitudes, and then you can do some observed magnitudes. And so the arrows go in that simulation order. And so this is exactly what I was going to say on this thing. Like, you know, what do these probabilistic models actually allow you to do? Well, they allow you to simulate your data, right? Because if you read this diagram, like I just told you, then that shows you exactly how to generate a realization from this data set. And so that's what I was going to ask you to do next, in the next horrifying task. So there's this Python notebook, okay, which we can have a look at. Exit. What's happening? Okay, yeah. Nice, good. So there's this here thing, right, which should allow you to do this, right? So this the Jupyter notebook just has a bunch of stuff you can import at the start, and then a little bit of setup. So I've assumed that we've got 2 galaxies, that each galaxy has 200 stars in it. You don't need to care about what that is. These are essentially the kind of fixed information that we need to care about. So this is like prior information on the absolute magnitude, priors on the slope. So these bars are the mean values, sigmas are the width of these priors, and then what the intrinsic scatter is. I've assumed that we've got the same uncertainties for all of the magnitude uncertainties and for all the distance moduli. And so then there's just this little Python function here, which is asking you to generate these quantities. So these are true distance moduli, true log periods, true magnitude, true apparent magnitudes, and then an observed distance modulus and an observed magnitude. Okay, and so these things for the rest of the thing to work, you need to generate them in this with these sizes. Okay, so you have one true distance modulus per galaxy, a true log period per galaxy per star, true apparent magnitude the same way, and then the observation. So the one thing that I've done differently here is that just the first galaxy has an observation on its distance modulus, okay? Because that's the kind of more typical setting. We have like one anchor for these things. We don't actually have independent distance estimates to all of these things. So this is, I mean, tell me if you don't want to do this. But I think it's kind of useful to show how you can translate, is it, oh, no. This diagram into a simulation, okay? So all you need to do is you need to do a draw from this distribution, do a draw from that one, and then for each galaxy, one draw from distance modulus, and then a draw from essentially the Cepheid period luminosity relation, and then the kind of likelihood steps. So do people feel like they have enough information to do that, or would you rather do it with me?
Well, we need to know what the functional form of
Exactly, right,
is
okay, so that's a
before
good
we
point. So assume that they're all Gaussian.
Assume they're all
Everything
Gaussian.
is Gaussian, okay?
If everything is Gaussian anyway, then you could fit your data analytically.
Boom, right, yeah, we can go through that just after this.
I
if you
just
want.
wondered.
Yeah. Yeah, so I've set things up so that everything is Gaussian, and this is, so again, I've fixed this so that it's known purely to make the next few steps easy.
The need for simulation is arising in the context of it's not.
Exactly. So everything being Gaussian allows us to show you, so I will show you how to do it all analytically, but then show you how to do it with different techniques that don't require it to be Gaussian at all. Okay?
What is the trend?
So is everyone happy, you know, with NumPy random, all that stuff? Okay. Well, so let's just do it for like 5 minutes and see how far everyone gets, and then I've got a cheat version that's completed, so we can just do that.
It's like a cooking show.
Exactly. Here's one I made earlier. Flash it. No, I can't. It's in there somewhere. But essentially, you're just doing a bunch of things. I don't know why I sorted them, but you're just doing a bunch of draws like this, right? Okay, so for your true distance moduli, you just want to draw n galaxy versions of these with the right sigma and the right mean. Okay? But let me leave up the, well, what's most useful to see? The network diagram or the code? You've got the code.
The network.
Thank you. And yeah, if anyone wants any help or like wants to ask more specific questions.
Why are we sorting this? Don't look too much.
Learning to like formally characterize it.
Oh, yeah.
Right, yeah.
Obviously, I have a lot of practice to do. But it seemed like it would be a nice improvement to have a different symbol for like measurement errors from population. Like little triangles, like the sigma sub ui is your prior on what the measurement error is, right?
This, yeah, well, so it's
And
the
it seemed like-
perfectly known uncertainty.
Maybe just add a circle around your.
Maybe, or something like that, or make it a little, yeah.
Sorry, say that
Just
again.
to distinguish between kind of.
Yeah, no, I tried that.
Population stuff, or, like, to me, the U bar and the sigma.
Yeah, no, I know.
Qualitative difference, and it was just, help break a, like a.
No,
reading
sure, no, I
degeneracy.
know. So this is.
Maybe it's Mrs. May calling you. That's what we vote.
Are people still there on Zoom? Oh, hello. Sorry. Are you... I broke it. I'm sorry. I'm going.
Somebody thought they were alone.
Are people there on Zoom?
Yep.
Nice. Person is there.
Oh, there's like 6 of us.
Ah, nice.
Can I ask you a question related to the Python notebook?
Yeah.
So I'm going through the one that I prepared earlier.
Uh-huh.
Bearing in mind this is my second time using Python.
Uh-huh. Cheating, I think it's called, isn't it?
There's an error in my pickled stand model,
Ooh.
and I don't know what that means.
I mean, have you run it all?
Yeah, everything else works.
It's because, yeah, so if you...
But my pickled stand model.
Yeah, so if you go through, if you set, you're about an hour and a half ahead. But if you set recompile equals true, and then it'll do it.
Where?
Near your pickled stand model.
I don't know what these words mean.
If you type true with a capital T, truer, and then, so now it's compiling.
Okay.
And so set it to false now.
Okay.
I need to change
Sorry,
that.
I just wanted to.
You're doing Hamiltonian sampling. Well, you're doing nuts.
So I'm eventually going to convert this
Is
to
modeled as
language.
Did someone, yes?
a Gaussian distribution around 1.
Okay.
In the shape of.
Oh yeah, so that's the log posterior. Not log posterior, log period.
Right, but I thought that was known.
Yes.
Python has you
So-
specify Boolean.
Oh yeah, where did I draw that from? Ah, that's a good point. So I didn't actually say what that.
Well, it's just NP document.
Yeah, sorry. So in my
No, is that
Yeah, I think it's by default.
in mine here, what's this? So I drew the log posteriors from so uniform in the range 1 to 2.
Okay,
So it's like 10 to 100 days. Yeah. Sorry. So that's that's something that's missing.
No.
supposed to recompile something, but then it's giving me a GCC error.
Oh, what's it doing now?
GCC's failed to work, but I have
nice.
GCC. I use GCC every day.
Have you got Stan installed?
I just did, yeah. And I restarted the kernel since I installed Stan.
That's good.
Yeah, I had that error too when I was trying
GCC failed.
GCC did.
Really? That's fun. Okay. Well, yeah, right. Okay, so you should use R, right? Okay, everyone should use R. So, how is everyone getting on? Anyone got anything that vaguely works?
So M true is going to be
Oh, sorry, I should have the network diagram on. Yeah, so for anyone who didn't hear that properly, you need these log periods to do this. And so what I did in my code was to just draw them randomly from in the range 1 to 2, okay? It doesn't necessarily matter what you draw these from, as long as it's, I mean, they're just numbers. So they can be whatever you want.
Sorry, I have a question about this. So are we also drawing for things in double circles? Because I thought those were observables, not things that
Yeah. So you're generating it. Essentially, the point of it is to generate this. So you're going from your prior information and generating all of the true parameters. So anything that's in either a single circle or a double circle is what you want to output in the end.
Okay.
You need the log the log periods as well along the way, essentially. So in fact, yeah, okay. Well, yeah, maybe I'll tweak that in a future version. Viviana, do you have a question?
I just wanted to check, so when we draw for a capital M star, I was just curious to see if the parameters of that distributions are the one called M star and M star.
Yeah, that's right. Yeah.
I was looking for something that started with M.
Yeah, no, sorry.
No, that's fine.
What are mu hat and m hat?
Yeah, so m hat is the observed apparent magnitudes. Mu hat are the observed distance moduli. And so for the rest of the code, I've just assumed that we only have one of these, so you can pick the first one.
Oh, I see. So like near true 0.
Sorry?
Yeah. Okay.
Yeah. Okay, so a couple more minutes and then we can see we'll see what I wrote.
Why is there an S true in the notebook when there's no S true in the network?
Oh, sorry, so S true, yeah, so that is S true. It's just S.
I see. So we're not simulating S in.
Well, we're drawing it from this prior.
Okay.
So we're drawing it from a Gaussian that has mean. I think in the code it's called S bar and then S sig or something like that.
But that's done outside of this function.
It's just that S true is an input to the function while we are simulating it in the function.
What have I written?
I think that's. So to be able to input as true, you
right.
need to draw first.
Okay. So for this, is that that's the way that I wrote it? Yeah. Okay. So for this case, you don't have to draw it. You can just take S true, and you can take abs true.
Is that something you recommend, that we simulate population parameters outside of these? Like,
no, that's a mistake in the function. Really, this should be, so really you should be drawing the whole thing, but for simplicity's sake, I just take the true value to be this. Yeah, okay, so I'll tweak the notebook so that you actually do that draw as well. Anyway, I guess we should probably...
Actually, in your second function, you have it right? Because you have simulate, and it draws from abs bar.
Maybe I just named it wrong. No, I only do the kind of observable part of it. Yeah, I'll tweak that. Anyway, so has anyone finished this? Probably not, because I buggered up the setup. But I think, is this supposed to finish at 11 or half 11? 11, right? So I guess we'll just kind of quickly, so this is what I have coded up, but obviously I've just shown that I've missed out the kind of true parameter sampling part of it. Once you've got this running, you can draw something from it and then just do a kind of quick kind of sanity plot for this, just to show that you've drawn these observations correctly. So this is just taking all of the... So the reason that I've asked you to return the true values for these things as well as the estimates is just so we can do some kind of checks. But this is just showing that we're simulating this. So this is showing the difference between the observed apparent magnitudes and the true apparent magnitudes to show that we have the correct kind of measurement scatter in there. So there's no intrinsic scatter in this diagram. But let me tweak that stuff the next time anyway. But so I guess that's a nice place to break it anyway. Let me just go back to these. So, so this is, I guess, what I've tried to show you today is, how to encode this structure in, encode the kind of inherent hierarchical structure of astrophysical problems into these network diagrams. Showed you how to interpret them and maybe draw and construct them yourself, and then showed you how if you set up the task properly, it allows you to simulate from your data set. The second half of the lecture is how to actually do inference with them, okay? And so this is essentially just reversing this arrow, okay? So when we're from simulating, we're going from top down. In terms of inference, we're going bottom up. So we're showing how to take our observed values and learn something about the parameters of interest. And so next time round, I'm not sure when Hug's going to let me do it, but I'm going to show how this actually happens, or how kind of data flow, or how information flows up from the data into the parameters of interest, but also how kind of features of these graphical models let you figure out what inference technique to use. And so, yeah, the point was made down in front here by Glynis that, in this specific case, assuming that all of these things are Gaussian means that you can do this all analytically. But in the case where these things aren't Gaussian, you have a bunch of different algorithmic choices that will allow you to do inference. And so, yeah, I guess I'll stop there for today. Cheers.